Today, we are going to talk about LangChain. I'm going to rewind back to something I showed you last class. If you look at all the different specialized models that are out there now, there's a lot of different tasks that different models are good at. So one of the things that they have done is they have done very sort of the instruction-tuned task-specific models. And those are the things that when you have a task to get done, then the model, the initial model is just going to dispatch it to one of these things. So this is what we call a mixture of experts architecture. And we're going to talk about how this is done, like an example of how this is done towards the end of this class. It's like, oh, you do the natural language understanding, and then from that, the model is like, I know exactly how to dispatch to whichever expert I know can handle your query. Now, this pattern is exactly the pattern that you see when you are building LLM applications on top of the model. So internally in the model, it's doing this. But then in this class, what we're going to do is the exact same thing. We're going to have a bunch of different like code implementations of things that we have built locally. And then our model or our application is just going to dispatch it to the things that are going to be there to execute the code, to execute that function. Okay, so I'm going to start with an example application. Here is old school ChatGPT. And like in 2022 or 2023, probably before a lot of you were even in our program, the bachelor students at least, we implemented a security elective. So ABET's like, yeah, in CS, you better have some coverage of security, otherwise you're not going to get accredited next time. So we're like, okay, it used to be you didn't have to take it, but now you have to take some kind of security elective. And so we asked ChatGPT, well, what elective is it? Like, are you smart enough to tell us? And then it's like, well, no, sorry. My last update, I was trained all the way up into September 2021. I don't have that information. Can't give it to you. Okay. So what we're going to use as kind of a motivating application is, can I build an online application that can update this with the current information that exists and then return a summary of it? So this is the goal, and this will be a lab that you do, not this exact one. I think this is the one I use in the cloud class, but like, yeah, can I get a chatbot that can answer this question accurately based on what it knows? And this is not even accurate because this image came from this software came from a couple years ago. We actually added 2 courses here. So for your undergrads, there's actually 2 more, but you get the idea. Okay, so this motivates, and we're going to use this application to motivate LangChain. So LangChain, I refer to it as an operating system for constructing LLM applications. Much like in your regular operating system class, you're building programs on top of the C library, which interfaces with the Linux operating system. I believe most of the applications today, LLM applications, are using this middleware, LangChain middleware, as kind of like the operating system for their application. So this particular package implements all of these different things: interfaces to LLMs, document loaders, document stores, prompts, and agents. Okay, so we're going to go back to our motivating problem. So after training, the LLM needs to incorporate new data somehow. So in order to answer this question, you have to take the vanilla model and do something with it in order to answer this question appropriately. One of the things that you could do, and this was the initial approach, is to do something called fine-tuning. You have a model, the vanilla model, that has been trained in a semi-supervised way with a bunch of labeled data to produce what we call the foundation model. This is the foundation in which you then say, I have a one-off application. Say, so in the cloud class, there's this ramen application. You have trained a vision model to identify all objects, but then you want a specialized vision model to identify particular restaurants' ramen. And then you're like, well, I have the pictures of the ramen and the restaurant that makes it. I could do a fine-tuning of that vision model to produce another model that can drill down and give me the actual restaurant that this picture of ramen was taken at. So that's the idea of fine-tuning. And this is what you would do. You would provide a whole bunch of labeled examples, And then you would take the foundation model and you would say, I want you to learn these new tasks. And then you have this task specific model that gets produced. And then you use that for your application. Now this costs money, like hundreds of dollars potentially, but it's much cheaper than actually retraining the whole model from scratch. And so Google has this service, it's called AutoML. They're like, if you're not a machine learning engineer and you want to be able to do fine tuning, Google says, just give us the labeled data set and we'll create this one-off for you. It's called AutoML. And they have AutoML for all of their foundation models. If you need a one-off, you just AutoML with the examples that you bring to it, and then you have your own custom model. So that is a thing. But that's expensive. And I'm trying to run this course without having to pay any money because I'm cheap. And so we want to do something different, which is approach number 2. So another thing that you can do is you can leverage the fact that models can learn with the context they are given. If you give the model enough examples and enough data, it can use those examples and data to give you a better response. They call this in-context learning. So the idea here is if I have information about the CS program and the security elective, I'll just throw it in there and say, hey, model, answer this prompt, and here are some extra information I'm going to give you. This is called context. So if you hear the term context engineering when it comes to LLM applications, this means delivering exactly the right amount of data and the right kinds of data to the LLM when based on the prompt that it's been given. That's called context engineering. So for example, you're trying to automatically do your CS homework, and you're like, here's my code base that's been given to me. I have to modify the repository to change a file that implements widget A. And then what you would want to do is you don't want to give the LLM the entire code base. It's like, well, I want the LLM to get the code that's related to widget A, and then to give that context to the LLM and say, modify it to implement this. This is what all these coding agents are trying to do. Like when you use Cursor or you use the Claude code, they are trying to do that. When you prompt it to do something, it's going to try and find in the code base the relevant pieces that it needs to change in order to implement what you asked it to. That's context engineering. I'm going to find in that code base, bring it in, make the change, and then hopefully get the results that I need. So this is really cool because you don't have to retrain the model, right? You just have to give it what it needs in order to answer that question. The model is used as is. So here's an example. What you could do is, all right, I have a user prompt. Tell me about the security elective. What I could do is I could take all the information on the CS department, the academic bulletin, the CS website, and I could just take that whole knowledge base and attach it to a context-aware prompt. And then I send this thing to the model. And then if the model can process all of this stuff and realize what the security elective is, can do the information extraction out of the documents I gave you, and that was the lab from last week, you're doing information extraction. If the model is really good at finding the needle in the haystack, this works, right? How many of you were surprised at the kinds of information you could get out of, like, you could get the model to extract out of the data that you gave? Did you give it like a megabyte worth of data and it found it, or anybody want to offer an example up? Okay. Yeah. Okay. Which one was that? Tiny Llama. Okay. Yeah. Yep. Okay. And you ran this on that hardware, the Llama server that, okay.
Like a court doc or a document from the House of Representatives, like one of those really lengthy hearings, and I was testing like the 4 gigabyte, I think it was long, but it was able to find a pretty decent amount. But if it was something really specific, like I had like find this term they use to describe AI, and it couldn't do it for Gemini 3.
Yeah, we'll talk about Gemini. So one of the reasons why people are using Gemini is because it can handle so many more tokens, and it can do this problem. In fact, Google advertises the needle in the haystack problem just because it has a competitive advantage over all the other models. But that's the idea. If you have Gemini, you can do this, and Gemini might give you the result. Okay, so that's the approach. So here's an example. The example, it's like using the description below. Same prompt, but I'm going to say using this description below, and then I dump out all the information in the CS program into this prompt, and then I send that to the foundation model, and then you get the result. You get this back straight up in ChatGPT. It like processes that text and then can give you this answer. But this knowledge base can be gigantic. And unless you're using Gemini, which we are in this class, so we could actually do this without too much of a problem, this is a problem usually. So we have like multiple degrees. We just popped up an AI degree. We're like minors, masters. We've got certificates all over the place now. So we had a lot of information about a lot of the stuff we're writing. We have all the information about all the courses that we offer. That's a ton in our knowledge base that we are sending in every single prompt that we want ChatGPT to answer for us. Okay, so this runs into some limits. So there are some context window sizes. And so for most of the models, you're at a couple 100,000. And then it's like, no, can't take any more, right? So that's a problem. And you see here, these are some limits. And in addition, when you provide all this context, sometimes, so if you take the LLM course from Amita, the thing that is the innovative thing in LLMs is this thing called the transformer. It's got this attention mechanism that allows it to focus on just the relevant parts of your prompt. It's an n squared problem, though. It scales with n squared, where n is the number of tokens. As soon as you start piling up the tokens, your performance degrades because of the n squared problem. And so then this is where needle in the haystack is so difficult with this model of doing LLMs, is because, yeah, the greater, it's a quadratic decline in your performance, your accuracy. Okay, so what we really want is we want to go from this, where we're dumping the entire knowledge base into the prompt and then sending it to the model. What we want to do is just to find the relevant documents. This is the context engineering part of this. I want to just find a subset that's related to my query. And then when the user prompts, when the user prompts me, I'm going to find the relevant documents, attach only the relevant documents, and then send that off to the language model and produce the result. So this motivates something that's called retrieval augmented generation. Now, there's many ways of doing retrieval augmented generation. I am going to show you one very specific way using vector databases. And I do this because I can show you all parts of LangChain with one app. But you'll see later on that sometimes, there's special cases in which you would do RAG in this particular way, and I'll get to that later. Okay, so in order to explain the vector database approach for doing RAG, I have to first talk about something called vector embeddings. So the idea of a vector embedding is that you take an object, like a large string of text, or a sentence, or a word, and you represent that thing as a multi-dimensional vector where each dimension has some attribute, some semantic attribute. So each dimension has a semantic axis, and then based on the semantic of the object that you are giving, it has different sort of magnitudes in each of these semantic axes. So here's an example. You take your words, paragraphs, and articles, and then based on your embedding model, it generates a vector, okay, with different weights that capture its semantic information. The idea is that objects that are similar are very close to each other in vector space. So here's an example. A sad boy is walking and a little boy is walking. These are close to each other because it differs by a single word. And then a little boy is walking and a little boy is running. They are also close to each other because they differ by one word. And then a sad boy is walking and a little boy is running, and they're a little bit further apart. They differ in 2 words. So you can imagine this across all of the different text patterns that you might have in your document database if they're stored as vectors. Okay, so now you have content and you have a vector representation of the semantic sort of meaning of that content. The next thing that you need is something called a vector database. You need a database that stores the original content and the vector that represents its semantic meaning. And this vector database will store both together. So sometimes they take a traditional database and they augment it with storing vectors. Sometimes it's a specialized vector database that stores both. Okay, So this is the way it works. I have a set of documents. And then what I'm going to do is I am going to split it into chunks. So basically you want the documents to be split up into discrete components that you can sort of, because if you don't split this up into chunks, then you haven't really solved the problem. You're actually, if you have an enormous chunk, if everything is one enormous chunk, then you haven't really zeroed in on the context that is really required to answer the prompt. So there is a chunk size that you have to optimize when you're doing this operation, but you chunk it up, and then what you would do is you would call an embedding on all the different chunks that have resulted, and then this is going to give you all the different vectors, the embedding vectors. And then you store it into the vector database or the vector store. And this is a picture of, in vector space, these are the vectors associated with the red, blue, and the green content that you have inserted into the vector database. Okay, so then the magic of a vector database is that you can query it to do a similarity search. You could say, here's a vector, give me all of the documents that are closest to this vector. And then the vector database is specially built to perform that operation quickly. Okay, so this is the idea. I have the vector of something I'm looking for, and then the vector database puts a circle, a radius around all of the points that are in vector space nearby this vector, and then returns those as part of the result when you query this vector database. Okay, so how does this help our original application? Well, this is how it works. So we have the documents that are in our knowledge base split up and stored into this vector store. And then what I do is I have a query. This is the user asking what are the security electives in the CS program. And then what I do is I take that question and I invoke the embedding, the exact same embedding that was used to generate the vectors for these. I send the question through it. And then I say, get the documents that are most close to this question I'm asking. Now you're looking at it and you're like, well, this is the question and this is the answer. So they're related, but they're going to be slightly different. Well, hopefully, because you're just doing a neighbor, sort of a rough neighbor match, you'll get the ones that are closest. And so in this case, if you take this embedding and you put it in this vector space, maybe it's right up there. And then you're like, well, the closest thing near that yellow circle is this red circle. And then I know the thing that might answer this question is in red, is the red split. Okay, so then the vector store says this is the relevant split and returns the red stuff back to the application. Okay, so this is the overall workflow. The idea is that you get a query and you want to go look in the vector database and pull the document that's closest in match to that query. So this is step one. You take all your documents, you split it up, and for each document chunk, you send it through the exact same embedding model. And then this is your vector, and then you store it into the vector database. That's the first step. Then you get a query from the user, and the user prompt goes to the exact same embedding model and then generates a vector for the user query. And then you use that to query the vector database, and then you get just the relevant documents associated with that query, just the red documents. And then you take this, you attach it to the prompt, and then you send it to the model and get the result. Okay, here's an animated operation that says the same thing. Document store goes into the embeddings LLM to go to the vector store. You have your chat interface. So like that chainlet interface I showed you earlier for the CS department's web chatbot. And then you send the query into that chat interface. That query goes into the embedding model. That searches the vector store, pulls out the information about the security elective. And then the information about the security elective is sent with the query into the base model. And then the base model generates the response. Okay. Questions about this application? This is your lab for this week. You're going to do all the different pieces of it. So you might as well just see this up front first. Okay. Yep.
What determines if it's close? The
vector distance.
Right,
yeah.
Right. But if there's like, how is that? Like if there's something just outside of like that dotted. circle? Like, would that be considered? What determines that?
So I don't think you specify a radius, but you'll specify a ranked. So actually, yeah, the internals of it, yeah. So then you'll get the closest one. Yeah.
I was going to say,
Okay, nice.
that number is off day.
Okay. Mm-hmm. Mm. So that leads me to your homework. You're going to build a custom RAG app of your own, and you can experiment with these kinds of things if you really want to focus on the vector database and implementing different things. So, for example, I showed this is just what the simplest architecture you could do. I just showed you, but there's all sorts of other ways of implementing RAG. So here's another one where, when the user asks that question, they might ask it in a strange enough way that doesn't look anything like the content that answers that question. And so one of the things that they suggest is that you take the user query and you reword it. You ask the LLM, reword this query in a bunch of different ways, hoping that the rewording will ultimately match the document that actually has the answer. So that's one way of trying to improve the performance. And then what you would do is all the documents that get returned on all of the rewordings, that is sent to the LLM to get the answer. But this is a lot of documents. Maybe it's too many documents. The other thing you could do is reword it, get the documents back, and then try and do some kind of ranking amongst the documents of which one is the closest, maybe a different kind of analysis, and then you send that to the LLM. So there is a whole repository of RAG approaches, and this is called RAG from scratch that LangChain has. So you could do any of this stuff. You could use different kinds of databases. Don't do an agent because agents are next week. But you could do all sorts of backend databases. You could do all sorts of different, splitting it up into different hierarchical indices. This is something that you can explore if that's what you'd like to work on for your homework for this week. It's kind of open. I'll talk about what I want you to do for the homework at the end of this class. Okay, so I just showed you a whole bunch of things that you're like, wow, that's a lot of work. And this is only 1 week. It's like, is this guy crazy? And I'm like, no, because LangChain is really the reason why LangChain is being used is that you could rapidly develop everything I just said using LangChain. In fact, there's like minimal amounts of code. And that's why I'm introducing this app and how this app is built in LangChain. And so I wanted an app where I could actually show you the stuff on the slides. That's this app. Okay, so LangChain has all sorts of features. Things that you would need for this RAG application would be something like a document loader. Like the content is on a website or it's in a PDF file. I need to pull the security elective content from the native format that it likes, that it resides in, to text because the LLM just likes text, right? I have to extract out the meaningful text out of these documents. I don't want to send the LLM all the HTML tags of the website. I want to extract out the meaning out of the website in its text. That's called that's a document loader. I'm going to load that document up. And then I'm going to chunk it up or split it up. That's, again, something that LangChain can do for you automatically. I want to invoke vector embeddings to generate the vectors for all the content. And then I want to store all those things in a vector store. So all of these pieces, LangChain makes it really easy for you to implement in your application. Okay, so that's the motivation. Now I'm going to go through just the mechanics. How do I do all of this stuff? What are the abstractions that LangChain is giving me to build all this stuff? Like, how do I program it? And that's why I use this figure, because this particular example is going to use everything except agents, which I'm saving for next week. Okay, so the first thing and the most important thing is how do I interface with models? And so LangChain, I mentioned last week, there's a standard chat completion interface that all of the OpenAI kind of standardized it and everybody copied. And so LangChain's like, oh, well, we can make your LangChain application model agnostic because everybody supports the same interface. And that interface, when you import it, is like LangChain chat models. Now, there are specific models that you get per vendor, but the idea is that every single vendor-specific model is interface compatible. It doesn't change the way it gets invoked. So that's the idea. Okay, so this is how you can, so that's that first week program. This is how you can get the same code to run against your open source Llama model, as well as Gemini models that are managed. And so this interface, this package allows you to seamlessly interface with local models like DeepSeek, Llama, Mistral, and such, as well as managed services over the network. So Claude, OpenAI, and Gemini. Okay, so that's the idea. And we're not going to go too much into it. We're just basically using the LLM as a black box, but that's it. The next thing is prompts. So you're going to need to manage the system instructions that you're giving to the application that you're using. And so here is what you typically would do is you would create a prompt template that is sort of all of the boilerplate that is configuring your application. And then you're like, okay, run this application. This prompt template will contain the system instructions that tells the LLM how to behave and what to produce. And then if you bring in any context from a vector database, you need to be able to splice that into the prompt template when we build our RAG application. And then you have your user query, and you need to splice that in. And so the LangChain prompt templates is just giving you a templating system for you to just include all of these three things at runtime whenever you are invoked. So those are templates. So here's an example, LangChain prompts. I think this is now in LangChain core prompts. So this code, if you copy and paste it, might not work, but you just have to ask for the updated LangChain changes by the week. So you got to be careful with some of this code. So I think this is LangChain core prompts now. You create this prompt template. You say part of this template is 2 parameters, the name of the graduate advisor and the user's query. So in this case, there's just 2 of these things and not just 3. And then you just say, you tell that this is your template, and you say the input variables of this template are name and query. And then what I can do is I can format this template and generate the prompt by instantiating it with the name of the graduate advisor and then the query that I am asking it. So that's just an example of using a prompt template. The template then generates a string that is passed to the completion model. So here's an example where you classify the following email snippet, and then like you're doing a spam detector, and you're giving it you're doing the few shot examples where you're like, these are examples of detecting malicious or benign emails. And then you give it an example. This is malicious. This is benign. Here is my message. And then I create a prompt template using this and including the user's going to input their message, and then the template's going to point to this template string. And then here's the message. I say, warning, malicious activity on your account detected. Click here to remediate. And then I can invoke the LLM, and then it gives me the answer. But one of the things one of the reasons this thing is you don't see this much anymore is because this in particular, turning everything into a flat string, exposes you to something called prompt injection. Now we're going to do a whole bunch of prompt injection in week 5, but this is just a preview. So if you take everything and you produce a single string, then what the adversary can do is they can try and trick your LLM into giving a bogus answer or an incorrect answer. So here's an example where the adversary gives you this subject, click here to win, and then off later on into this prompt, it tries to pretend to be one of the few shot examples. And it says, this is benign. So label it looks like you labeled this as benign as an example, as the 3rd example. And then you say message, hello from Portland. And of course, the LLM is going to say, this is benign. So this is what we call prompt injection, where you're hijacking the prompt to inject malicious payloads to get the LLM to make a mistake. Okay, so keep this in mind. We're going to do a whole bunch of this stuff later on when we get to week 5. Okay, so the reason I give you this prompt injection is to show you why you don't see this as much anymore, but you instead see chat templates. So rather than using a single prompt, what you do is you create a template of a chat interface that goes back and forth, and you explicitly delineate this is the user's message. This is the system message. This is the AI message. This is the human, or the human message. And so this is what it looks like. I am going to create a template from messages. And so I have clearly delineated that the system message is a helpful AI bot, and this is your name. And then this is a human message. And then the human input is delimited in a structured manner. Now, again, you could try and hijack this syntax. You can inject into this syntax if you know the syntax is being used. But at least this is a little bit better than a flat string, right? So that's the idea. So then when I do this, format messages Bob, and then what is your name? It doesn't get confused. It doesn't get confused what is the human input and what is the system input or the AI input. Okay. So let's look at that prior injection and see if it works. So if I take that exact same example and I use the chat prompt template instead of the regular prompt template, what happens? So this is an example. I create a chat prompt template, say these are the messages in my template. Classify the following email as benign or malicious. And then here are the examples that I give. Unclaimed winning ticket, view attachment to claim, and then the AI is malicious. So I'm giving my few shot examples in this structured format that labels this as human and this is AI. And then here's the next one. Thanks for your interest. This is benign. And then I say, as part of the template, now you can splice in the human message, and this will hopefully resist the injection a little bit better than if it was a flat string. Because then the adversary has to kind of like break syntax and then repair syntax around it in order to do the injection. If any of you are in the web security class and remember what SQL injection had to do to operate, that's basically the same thing in this case. Okay, yep. It all gets converted to a flat string, so that's actually injectable. And this is why prompt injection is a forever bug. Forever. Like, don't rely on the LLM to do anything security related, like even detect an attack. It just can't do it. It's not built for that. So, but that's a soapbox for week 5 that we'll talk about. Okay, so then this is the adversary. Maybe the adversary knows the format of this chat prompt template. So it's sitting here trying to like, I'm going to try and break syntax here with a single quote and a parentheses, and then I'm going to inject the AI thing, and I'm going to inject another one that says message hello. This is replaying the exact same attack, hoping that these boundaries will get interpreted by the LLM, and then it wins again. So that's what you're referring to. And then, of course, in this particular example, the LLM doesn't get tricked because it gets converted into something different and with a different framing. So then in this particular case, the human, you can see at the bottom, I've kind of parsed this out and then formatted it so it's very clear. But this all is considered the human message, all of this stuff, and then this is malicious. Okay, but your mileage may vary. Like all the exercises in this particular class, like sometimes they just don't work anymore. Like you could try this again and it might actually work. Yeah, it depends on the model. All right, the next thing I want to talk about are chains. So simple applications would just invoke the model directly, like we saw in the earlier ones. But when you start building up functionality and you're starting to use all of the different abstractions that LangChain provides you, then typically one pattern of building an application is to take all this functionality and represent it as a chain of functions that you just send the prompt through. And then it goes from one link of the chain to the next, from the input to the output. Okay, so this is a pattern that LangChain was like, we want to make this super concise. We want to build something that allows us to express this functionality in a single chain that can be defined once in one part of your program and then just invoked everywhere. So they developed the LangChain expression language to encode this kind of function. So one of the things with this expression language is that all of the input between links of the chain and output is in JSON. So everything is JSON that goes back and forth. And this is fortunate because, as it turns out, if you look at how agents are built, all of that is done with JSON. When you invoke tools and you get the results back, that's all JSON. So everything internally is basically JSON. So that's just forward referencing what you'll be dealing with. Okay, so we have a very simple application that we've been looking at. We have a user input that goes into the prompt template, and then that goes into the LLM. So this is an example of using the chain, of defining a chain. So I create a prompt, tell me a joke about this of a particular subject. I instantiate the model, and I create this chain that says, take the input, go through the prompt, and then take the output, and then just send it to the model. And then what I do is I just invoke that chain with the subject that the first part of this chain requires as an input parameter. And so I invoke it with JSON. So there's a dictionary, basically, where the subject key is set to bears, and this is just tell me a joke about bears, and then I print the content. Okay, so why don't bears ever wear shoes and they prefer to go barefoot is the answer to that one. So this is what gave LangChain its name. This is what I refer to, this is an opinionated approach for constructing LLM applications. And there are people who hate LangChain's opinion, and they're like, don't build anything on LangChain. They would rather just build their own stuff. And if you're in this age of vibe coding, and in this age of rapid development, maybe you could regenerate what LangChain does on your own. But we're going to use LangChain because it's out there and it's easy, and all my code examples are using LangChain. But there's other frameworks that are out there that people are using, and you'll probably come across some of them. But we'll start with LangChain first, and then you can do other things. Okay. The next thing I want to talk about is memory. So if you have a chat application, you have to keep the conversation history. The model isn't going to keep it for you. And so the way it works is that you have a chat, and then you keep all the messages and responses that you have gotten in that chat, and you're sending it back and forth between the model all the time. The model is stateless. You bring all the state into the model. And in order to do that, you need some way in your chatbot to store history. And this is what conversational memory is. So this is an example. If you have an application with conversational history and you ask these questions and all of a sudden you say, oh, what was I wanting to know about initially? Then if you have the whole replay of the conversation, you can get a response. Whereas if you don't have the conversation history, it's like, I have no idea what you're talking about. Most of my programs are on the right because I'm like, when I want to show you something, I don't want to show you a whole bunch of other stuff at the same time. So I'm not implementing conversational history unless there's one lab where I do a chatbot, but that's the only, if you need a chatbot, a full-on chatbot, then you would look at that lab and how it implements conversational history. Otherwise, all the examples here are stateless in my class. Most of them are stateless in my class examples. Okay, so here's an example of using memory. I have a message memory. So I want to implement the conversation history, and I'm going to attach the conversation in between the system prompt. This is now the history of all the messages that came back and forth, and then the actual prompt that the human just gave me. And this will implement your chatbot as long as this history variable has that whole message list of all the prior messages that have been sent back and forth between the model and the human. And then I create this chain that says, go to implement this prompt and then send it to the LLM. And then here is where I have this in-memory vector history store to store all the conversations across all of my users. So if I have a web interface like the CS chatbot does, and I have multiple users hitting me, then what I need is a sort of a conversation storage to hold all of the conversations at the same time. And that's what we're doing here. And then what I can do is, if a user has a particular session ID, so they're using my chatbot, I've established a session ID, like on Python Flask, there's a session ID to say, oh, this is how I'm going to track your conversation and keep it separate from someone else's. Then I can use this is basically a dictionary. that's indexed by the session key, which is the session ID here. And then what I can do is when I create the chain, I say, I'm going to create a chain where this particular user, I'm going to create this chain with a history, the user's history based on a session ID, and then take as input the user input, and then pass in the history using the history key that will place the user's messages in there. And then when I'm interacting with the chatbot for a particular user, say I authenticated with OAuth, and I know that the user interacting with my chatbot this is my email address, then what I can do is I can retrieve the history based on my session ID, and then have this fill in this history, the get session history based on my session ID, and then get the context aware, or the history, the conversation aware prompt back and forth with my chat application. So that's an example if you need the conversational memory added to your application. Other questions about this example? Yeah.
I guess, so like when you're using like the user interface for like an LLM, is it stored in like the browser, or is
it could be stored in the browser, but typically it would be stored on the web server that OpenAI, like ChatGPT has got the web interface, because when you revisit ChatGPT, it has a history of all your prior chats. So there is a database. This is why data breaches at LLM companies are a big deal, because it's got your entire database of chats, so that when you revisit ChatGPT from different devices, you can still get your conversation history. So there is some database that's storing all your interactions. And then that's basically your session ID. So then when you go and you load up a prior chat, it's got a different session ID. And then on ChatGPT, if it's built using LangChain, which it's not, but like it would pull that conversation history based on the chat that you're interacting with, and that would be the conversation that goes up. So you can, reclaim the context immediately by just sending all the messages. Yeah.
I just sometimes when I ask Papa wants to store it
Locally? Okay, yeah.
Yeah.
Yeah, maybe on the phone app, is it on the phone that it asks you to do this? Is actually the desktop. Oh, that's interesting. Yeah. I don't know why they would do that, but yeah, because your web browser isn't interacting directly with the model. I think it's always done through the web interface. But yeah, I don't know why it would do that. Okay, the next thing I want to talk about is something called LangChain Hub. This is a repository for where people have published useful artifacts that other people want to use. This is like GitHub. If you publish useful code that I want to use, here's the GitHub link. Same thing with LangChain. You have a useful prompt. I just want to use it. I don't want to write my own. I'll just call the hub with this. So here's a common prompt that's used for a RAG application. The RLM RAG prompt, I'm like, I don't want to write my own, so I'll just pull it. And if you pull the prompt and you print it, it's like you are an assistant for question answering tasks. Use the following context and answer the question. And then you have placeholders for the user question, and you have placeholders for the context for the RAG part of it, the retrieval, the document retrieval context that you put in there. And then that's the prompt that you'll end up using. So if you don't care to import LangChain Hub, you just copy this and just copy and paste it into your own chat prompt template, and then be done with it. Which is, I just wanted to show this to you because some code will have this, and you'll be like, what is that? I don't use this a ton. I actually handwrite most of the prompts, or hand copy most of the prompts from somewhere else. Okay. All right, the next thing I want to talk about are document loaders. There are many kinds of documents out there. There are many document formats. There are many document locations where the information is stored at. And what you want to do is you want to make the application developer's life easier by allowing them to easily load all the documents in all the locations in any of the formats that are out there. So that's the idea of the LangChain document loader. This is actually why I think it's going to be hard to move off of LangChain, because they have such a large quantity of document loaders. It's like you would definitely use LangChain for the document loaders, even if you skip all the other stuff that LangChain provides. Okay, so if you have taken a data class, one of the things that people talk about is an ETL pipeline. This is extract, transform, and load. You take your raw data in whatever format it is, you extract the relevant information, and you potentially transform it into a more useful form, and then you load it into a database. So you can think of document loading as something similar to that, where you're going to do this operation and load it into a database somewhere, a vector database. So this is a picture of all the different kinds of data formats and data locations that are implemented. And this is just a tiny subset. You can actually go to the LangChain page, and it's literally like, many dozens of loaders that are implemented in LangChain. So you have any kind of data format, and this is going to be for your homework. Like, I want you to find a data format that's not implemented in your labs and add it. And then another option is to create your own. Like, maybe you have a document store. Maybe it's your file system, like you have notes, and then you create a loader for your own document, your own custom loader. That's what you can think about doing. But yeah, you can leverage any of the loaders that are out there, any of the different locations, any of the different data formats, either unstructured formats or structured formats. All of this stuff is there for you to potentially utilize. Okay, so I'm going to give you some of the loaders that are in your lab. The easiest ones are the web loaders. So web content, where you're going to a website, you're extracting out you're getting rid of all the tags that are not relevant to the website, and then pulling out the useful semantic content, and then giving that to the LLM. So that's what the web-based loader, the async HTML loader. And then if you want to do a recursive download of a site to get all the documents that are like, this is for the CS department website. Well, yeah, I'm going to do a recursive loader on the website to get all the documents of the department into the database. And then you would use one of these recursive loaders. There are loaders for optimized web content. So things like Wikipedia and the archive, which is just like preprint papers, they have specific format of their website and information, so they can do something custom because they have so much information. It doesn't make sense to just throw a generic loader at it. I can pull extra semantic information and more accurate data if I create a custom loader for these particular websites. So those are two that you use each one of those in your lab. And then local documents, so text files, PDF files, Microsoft Word files, Markdown files, and then CSVs. These are all implemented as part of the loaders that are in your lab, at least. Okay. And then another one that's implemented in your lab is a GitHub loader, or I think it's not a GitHub loader. No, it is a GitHub loader. I give it a link to a GitHub repository, and I say, load that up into the document store. I want to ask questions about my GitHub repo. And so there's one of those as well in the lab. Okay. So as part of loading the document, we need to now talk about what do you do? Well, how do you do the ETL part of the loading of the document? And so the two operations that I want to talk about are the transformation operation and the chunking operation. So the first issue is that the documents that you download often have a bunch of formatting and code that's not related to the semantic meaning that the LLM needs. The LLM doesn't need all of your HTML tags. It doesn't want them. But you got to get rid of them if you want to load it up. If you want to just pull out the semantic content, then you got to get rid of them. And that's a transformation. That's one transformation you could do. And so I think in the lab, we do a Drupal transformer. So the university website is running Drupal, and all of the Drupal semantic content is in the article tag in HTML. So there's a transformer that says, just pull out everything related to the article tag, and then make that that's how you do the loading. You do the load and the transform to get just the semantic content out of that. Another problem is that if you're downloading a document like the academic bulletin at Portland State, that's way too big to just send that into a vector embedding. And so you need to be able to split that large amount of text or a large amount of data into smaller chunks. And that's basically what this is, the chunking part of this thing. So recursive character text splitter is a way of intelligently chunking the document so that the boundaries aren't crazy. So you'll see that, you could just say every 100th, 100 byte chunks, but then your boundaries are all messed up. What you want to do is to do a chunking where the boundaries are kind of like at least sentence boundaries. And that's basically like what that's doing. It's trying to chunk this thing up so that, what you want to avoid is a semantic sort of crossover that's the boundary is crossing a chunk because you didn't chunk it up nicely. So that's the idea. Okay, so here's an example site, ChunkViz, where you can get a visualization of how things are chunked. There's many different algorithms for doing the chunking. Here is one that's very specific to Python code. So when you go and you use a coding agent, and somehow it knows Python really well, it might be the case that the chunker or the splitter that it's using knows about Python syntax and will split up the chunks so that they don't cross Python lines. So this is an example. You give it a program and it knows exactly how to chunk it up so that the code fragments don't get split. You don't split right in the middle of a Python statement. So that's an example. So I don't think I have you run this, but if you go visit this, you can actually copy and paste a bunch of stuff and see how things get chunked. There's a drop down here. So you can actually experiment with a bunch of different algorithms. Okay. The next thing that happens is after you chunk it, you basically do something called tokenization, where the model doesn't like actual raw text. What the model is doing is it's taking your text and mapping it into integer tokens. So when you hear about token costs, the tokens that they're talking about is this mapping that takes these particular words or sentences and maps them into integers. So this is how the training of models happens. It's in the integer domain. So everything goes into a neural network that's basically run by integer numbers that are mapped to the original text that was used to make this translation. So this is what they call tokenization. And it gives you efficiency and compactness when you're doing the training of the LLM. Okay, this is often hidden to the developer. Like when you're building your applications, you'll never go to this level. I'm just showing this to you because when you're like token cost, what's a token? You'll know what a token is now, because this is a good picture of that. Okay, so this is an example where the token is mapped to a single word, but typically you can do subword tokens and you can do multi-word tokens. And so the model itself, the foundation model, gets to choose how it does the tokenization. So that's something that's model specific. Okay, so this can be done in all different kinds of ways. So across sentences, from words, subwords, you can actually play with the OpenAI tokenizer. So this is the name of the tokenizer that it uses. Where is the name? Oh, the name's not there, but like you can actually use the exact tokenizer that's being used to train the models that OpenAI uses. And so you can type this in and you can get the number of tokens, and you can actually see this is doing subword tokenization in order to generate the mathematical representation of the text, the integer representation, the numeric representation. It's doing subword tokenization for the OpenAI tokenizer. I just wanted to give you that as a visualization of what's going on. Here is this really cool tokenizer web app. You can experiment with all the different types of tokens. So this is DaVinci. And then it also is doing subword tokenization. And then you can actually get the integers that are coming out of this. And then this is the same kind of operation that's being used in the vector embeddings, right? Like you're going to basically map this thing into a bunch of integers, and then you do the operation on integers. Okay. Your lab will go through and pull out the actual tokens that you're sending to Gemini, I think. Either Gemini or OpenAI, I forget. Okay. And then you can see there's a whole bunch of tokenization models. It depends on the model you're using, and you can experiment with those as well, if you'd like. So that's the link to it. So it's important to note that your model usage is billed based on the number of tokens that you are sending. There are a number of input tokens. That means it's the tokens you send to the model. So if you're sending one enormous chat back and forth and you're not using a new model or a new chat, like for every new distinct conversation you have with the model, you should create a new chat, because otherwise you're sending a whole bunch of input to the model that you have to pay for, right? And if it's not relevant to the actual thing you're asking, you're incurring input token costs. Likewise, if you're asking the model to produce a whole bunch of output, that's also getting charged at this level. And this is the unit of billing that's going on. Okay. So the next thing I want to talk about, is embeddings. So what the embedding process is doing is it takes your tokens and it maps it into a vector. So it takes basically one vector, which is your one vector, which is your token sequence, and maps it into another vector, which is the semantic meaning of that string of tokens. So it's all being done at the numeric level. And so here's an example. I say the payload is malicious, and then I produce a vector embedding in n space that's got all these attributes that says this is what that sentence represents semantically. And that's the embedding that I mentioned earlier. And so we're going to do these embeddings in order to do the similarity search when we do the vector database lookup. Okay, so this is what it looks like, one visualization. Vector embeddings and then n space for similarity searches. I don't know where I pulled this image from, but I thought it was kind of cool, so I left it in there. One of the things with embedding models is that you have to know a little bit about the domain that you're using to do the embedding. Sometimes different embedding models are best suited for different kinds of data. So there are image models, there are audio models, and there are text embedding models. And so if you have the CS department content, which is all text, you would use a text embedding model to do the embedding into a vector database, which is what you're going to do in your lab. Okay, so all of these vary based, so these different models have different performance. And so typically, if you want to look at the performance, you go look for a benchmark. And so Hugging Face has got the benchmark of, in this case, multilingual text embedding. And then you can see all the different models and sort of their accuracy over a particular benchmark. So all of these models also vary based on price and runtime performance. So you want a cheap embedding model that's accurate and then runs fast. And so we're using the Gemini embedding, which is super cheap and relatively accurate and relatively fast. Definitely cheaper than, well, I guess it's cheaper if you run it on your own. But we're going to be using the Google ones, the Gecko one in our case. Actually, this is 2023. It's cheaper now. Okay. In terms of actually using an embedding model, one of the things you can do, just like in your Llama lab, you can run a model locally on a VM, or you can run it, you can point it to a managed service. The embedding model is the same. You could actually spin up an embedding model on a GPU, and then you could say, I'm going to do the embedding locally, which is what Hugging Face has got a whole bunch of embedding models. In fact, these are CPU embedding models, so you can actually run it on your regular CPU, not necessarily your GPU. Or you could be like, you know what, I don't want to run anything. I'm going to just use the API. So in your lab, there's enough moving parts in your lab that I'm like, yeah, just use the model, the managed model. So you're going to just use Google Cloud's Gecko embedding to do your vector database, your RAG application. Okay. So I'm going to show you how this embedding works to do this router chain that I referred to earlier. I'm going to use the embedding model to do a task dispatch and send it down one of these, down one path or another path. Okay, so this is how it works. Well, this is what we want. We want, if the user input is write a Python function, then there is a route here that has the Python expert, the Python code generator expert. If the user says write a poem, then I have a chain that has all of the poetry integrated into its chain to answer this poem generation. If I ask it to explain a concept in quantum computing, maybe I ask Wikipedia. If I say generate an image, and then I would go to an image model. And this is basically what you see in ChatGPT. When you say generate an image, it will dispatch it to this thing and then return it through the web interface. And then finally, a question about legal, the differences in the UK and the US, and it was have some kind of legal expert chain on the bottom. Okay, so we are gonna just do a toy router chain using these embeddings that I just showed you. So I have two chains. One is a math expert and one is a physics expert. And the router, the input goes to the router chain, and the router looks at the subject and say, what is it most similar to? Is the input most similar to something that's in the math chain or something into the physics chain? And then I'll implement the dispatching. This is just the hello world of embeddings. So here are my two chains, and the only difference is the prompt template that's being used to run these chains. So the physics template say, you're a smart physics professor, answer this question with your knowledge, and then the other one's the mathematician one. So these are the two templates. And then what I'm gonna do is I'm gonna create embedding models or embeddings for each one of these templates, right? Because when the user asks me a question, I have to see what the question, like, is the question most similar to the physics template or most similar to the math template? So I'm going to create an embedding. I'm going to take all these prompt templates, these two prompt templates, and I'm going to create a list of embeddings for these two templates. And then I'm going to implement this prompt router that takes the user input. And then I'm going to create an embedding for the user input. And then I'll do a similarity match. So cosine similarity gives you the distance in between the query embedding and the other two embeddings, the physics template embedding and the math template embedding. And then based on that, I will either select the math or the physics and then route the thing thusly. So then this is my LangChain implementation. Given the query, go through the prompt router to figure out which of these two prompt templates to use, and then send the rest into the model. So it's just emulating a router chain using embeddings in this case. So at the micro level, this is kind of what's going on in a modern sort of ChatGPT service. Okay. I will take a 5-minute break, actually. I thought I could get through this without a break, but no, I'm getting tired, so I need a 5-minute break. And I'll finish this up with the vector stores and then talk about your homeworks, or your labs and your homeworks. Yes, I'll do that too. Okay, I'm gonna finish up. Just got a little bit left, and then I can let you guys get to work. The last piece of this, or the next piece of this, is the vector database. So we talked about the embeddings. We talked about the document loading. We talked about the tokenization and the chunking and the transformation. And then we talked about the embedding. And now we're gonna do the vector store. So we have to be able to store these embeddings. And again, this is just one way to do RAG. There's other new, hotter ways of doing it now, but this is the canonical example I'm gonna start with because it's the easiest one. So the vector database, if you recall, stores these vector embeddings, all these purple things, and then it allows you to do a nearest neighbor search. If you give it a particular vector embedding, then it'll pass you back the top K sort of candidates that are closest to that vector embedding. Okay. Let me get my cursor back. So just like the embedding models, just like the actual models, you could either run the vector database locally, which is what I have you do in your labs, or you could do a managed service for it if you don't want to manage all the documents in your own database. So again, if you want to do your own local open source vector database, Postgres, which is your traditional SQL database, they added support for storing vectors along with the documents in that database. So this is PG vector. And then there's all sorts of, there's like a like a whole bunch of different open source vector database products that got the projects that got released. So ChromaDB, Facebook AI Similarity Search, LanceDB, and these options. So we're going to use ChromaDB in this lab, but you could plug and play any of these other vector databases as you like. So these are these dedicated vector databases, but then again, if you already have a SQL database with a bunch of like a document store that's been implemented in a SQL database, you could add vector support on top of that as well. If you don't want to store the vector database locally, if it's enormous and you want to use a managed service so that like maybe you just want Google to back up all of your vector database information and you want to actually run the embedding, you could do these managed services. So Weaviate and Pinecone, these are startup companies that are doing this thing. Elasticsearch has a hosted operation as well. What is it? So Google has their vector search service. So I'm not having you use this, but they also, if you want managed vector databases, you could do that. Okay, so what I'm going to do is walk you through the construction of a RAG application. It's basically going to do this. It's going to take your question. It's going to, well, first, it's going to set up the vector database by loading all your documents into the vector database. Then it's going to take your question, send it through the vector store to get embedded and then get the relevant documents back. And then take that question and then add it to the prompt template, use it to include in the prompt template along with the relevant documents, get included in context. And then that gets sent to the LLM, and then the LLM sends it to what we call a parser. I'll talk about parsers later, and that generates the answer. So that's the application that we're going to build. And here it is on one slide. Well, the main pieces of this in one slide. This is what it looks like. This is my template. Answer the question based on the following context, and this is the thing the vector database is going to splice in. Here's the user's question, and then the user is going to the user prompt is going to get spliced into this location. Here is my prompt template. I'm going to say the two inputs. One is context that's filled in by the vector database. One is the question from the user. I instantiate the model and I say retriever, vector store as retriever, and this is the vector search that's going to be used for any question that gets sent. It's going to retrieve if I just invoke the retriever, it's going to pull out the relevant documents based on the question. And this is my LangChain chain. I'm going to get the context filled in from the retriever. I'm going to get the question in and then just pass this along to the prompt template. So this is populated by the vector database. This is just taken from the user input and then sent to the prompt. So then the prompt gets both this context and this question filled in, and then it creates this, and then it sends it to the model. And then there's a stir output parser, which I'll talk about this in the next slide. And then you invoke this with the user query, and that invokes this chain with this input to get the result. And then you print, oh, I don't have the print statement there, then you print the result. And then I can invoke this chain again with other input, and it'll go through this chain again. So this chain is like a variable, and when I invoke it, it just sends the new user prompt through that entire chain of functionality to produce the result. Okay. So that's it. And basically, I mean, you look at the code, that's effective. I mean, there's some stuff that I removed, but that's effectively all of the key parts are done right in this one slide. Okay, so we look at this and you're like, what is this stir output parser? So one of the things I mentioned is that everything that goes in between these stages is JSON. And the last thing you want to do is read JSON as the output from a chatbot. Now, some of the programs that I have you run, I don't parse the output. I actually want you to see the JSON that comes back because there's all sorts of other attributes like the number of tokens, for example, and all of these other kinds of metadata that come back as a response from the model. I want you to see that, like, because you have to be able to reason about what the model thinks you're doing in order to really optimize the performance of your app. So it's important to note that for a regular user application like the CS chatbot, I only want the output. What did the model actually spit out? I don't care about any of the other stuff. But if I actually want to study the costs and the token number of tokens on each one of these queries, then I would actually have to poke into this JSON that comes back from the model. Okay. So that is what a LangChain, the LangChain parsing package implements. It does this data marshaling between parts of your LLM application. So from the user to the application, and then from between the application steps, between the chains in your LangChain application, and then from the application back to the user. You have to get the output and the input in a format that you can actually use. Okay, so one of the things that is noted here is that if you're doing your communication all in JSON, the model has to be really good at sending formatted JSON that's structurally valid between steps. So what happens if one step gives you JSON that's malformatted and then the other step can't parse it? You got problems. And so LangChain has this specific JSON parser to try and make this more deterministic. And so you'll see when you're running your LLM applications, it's so non-deterministic. So much stuff goes off the rails that you have to do stuff like this to try and coax the LLM into proper behavior. So that's the idea. So here is an example of the one I just showed you in that other slide. It's the stir output parser, and it does something really dumb. So in between, the model is going to return something like this, something similar to this. It's basically a JSON object that says, this was the input you gave me, and then this is the output I generated. Now, you could just take it from the model and print it out on your screen, and then hope your user likes parsing JSON. Or you could say the user only cares about the output. So what stir output parser does is it goes into this JSON object, figures out where the output is, and then just prints that. That's all stir output parser does. You could have written that, handwritten it in JSON or in Python, but whatever. This is a structured way of handling the parsing in between stages. And we do this because there are other more complicated parsing things that we also want to do. And if we have this one mechanism for doing it, it's straightforward. It's the same kind of syntax over and over. You look puzzled.
Are we actually having the LLM as JSON then, or just
the LLM will return this.
the entire?
Yeah, the whole JSON. Actually, way more. This is fitting on a slide. I didn't want to give you, but there's like a whole bunch of stuff there. And then you have to pretty print it, really, because it's just a run-on JSON string. And you're like, oh, okay, like you could pretty print it and then actually see all of the structured objects. Like here, it's not too bad. You can see that there are only 2 keys in this JSON, but like I edited this so to print it on a slide so you can understand it. But there are examples, I think in this week's labs, I'm just gonna dump the JSON so you can see. I want you to actually see everything that gets returned, because you never know when you actually might want to know those pieces of information. And if you already know that gets passed, then you can, instead of calling stir output parser, you could call your own parser and get the other fields out of the response from the model. Okay, any other questions about that? You'll see this there and you'll be like, what is that? It's something really, really simple. Okay, so something that is more useful is the JSON formatted input and output. And so if you want your application to generate well-formed JSON that fits a schema, then you would use this JSON output parser. And moreover, when you give it this parser, you specify the Pydantic schema that says, make sure whatever you output is adherent to that schema, right? So you're trying to get the LLM, you're trying to coax the LLM into learning JSON and to get valid JSON that fits a particular schema. So in this case, this is a movie example, and I want the LLM to produce a movie, a set of movies, where the object that gets passed back fits this schema. So you want the JSON to have 2 keys. One is a genre, which is just a string, and then the next is the movies, which is a list of movies in that genre. And so what you do is you say, I want this JSON parser to know that the actual format of the JSON to adhere to is this schema. So that's why so Pydantic is a type checker for Python. And that's really, it's basically a contract. It's like a type contract for data structures that you're using. So this is an example. I want the output that the LLM produces to adhere to this JSON schema. And I've just told you what it is up there. Okay, so here's my JSON prompt. This is my prompt template. Find the top 5 movies of the genre given by the user. And then this template is going to include some formatting instructions that will encode what the JSON schema is. And then it says this is the genre that's given by the user. So that's given by the user. Now I'm going to fill in the format instructions by invoking this JSON parser to get the format instructions, to get the text description that describes this class, describes this schema. And so what happens when you create this, the LLM is going to get the text version of what it needs to do to format a proper JSON. And by doing so, you are praying that the LLM can understand these instructions well enough to always give you a well-formatted JSON output. And this is how you guarantee it. So if you see the JSON output parser and you see a schema in there, that's how you are rigidly trying to get deterministic behavior in your LangChain application with JSON. So it turns out, like, I didn't teach this the first couple of times I offered this class, and like students were like, yeah, this thing is failing right in the middle of my application because it's like a malformatted JSON. And so like, because the LLM is non-deterministic, sometimes it just randomly gives you what it thinks you want, and you need to tell it explicitly what you want. So with all LLM applications, you have to be very specific with everything. Otherwise, randomly, it will produce something that will crash your entire program. So that's the frustrating thing with developing these applications. And then your chain is you create this JSON prompt. So it gives the JSON prompt the formatting instructions. You pass that into the LLM, and the LLM, because it has the format instructions and the genre, can pass that to the JSON parser, which then just pulls that thing out. Okay. And then you do this invoke genre comic book, and then you get the JSON output that is exactly what you specified in that class. Okay, so that's it. That's all the things I wanted to teach you about LangChain aside from agents, and I'll do agents next week. But for this week, I want to now allow you to get a head start on all your labs and your homework. I'm going to very briefly talk about your labs. The labs are a tour through LangChain. All the different things I just rifled through, there are small code snippets that you just run all this stuff, and then you look at the output. So that's the first part. So 2.1, 2.2, and 2.3 is basically everything I just talked about. And then your homework is to do something creative on your own. You can extend it. You can extend the RAG application with your own RAG architecture. You do different documents. You do a custom loader. You do other built-in loaders that are in the LangChain documentation, and then build something unique. So that's your homework. These are the sort of the options for building your own RAG application. Submission. The code gets submitted in GitLab. A 5-minute walkthrough. I'm hoping I have enough time to do this every week, is to watch your 5-minute walkthrough. And the walkthrough, what goes in the walkthrough, the instructions are very detailed in the write-up. And it's really important that you go step by step through that walkthrough when you're doing it. One of the things I would mention up front is that I know a lot of you are just going to generate a bunch of code from ChatGPT. It's really important that if you're going to use that, you better understand every line of code that gets produced, and you better describe that in your screencast. Otherwise, I'm deducting lots. So I can't prevent you from using an LLM, but I can make sure you understand every piece of code line of code that you submit, which I actually think is the most valuable thing you could be training right now, is code validation. So you are practicing code validation to me, which I think is useful. I mean, the generation is the generation now, but being able to vet the code that comes back and get it to work and explaining it to me is what I am looking for explicitly. So if you are thinking that I'm looking for a large quantity of code, that's not what I'm looking for. If you can submit a large quantity of code and explain every single line of it in 5 minutes, that's one thing. But I am looking for code that you understand, that you can show me you understand in these projects. Okay. Any question? Hopefully those instructions are explicit enough that you understand what I'm looking for. Yeah. Yeah, Monday night with the lab. So the Git repo is going to have your source code and then a link to your screencast, a URL. So if you follow the directions, there'll be a text file. And try and use the exact naming that I have there, because I try and script the collection of all of your URLs. And so people are using different names and then I can't find it. And it just, yeah, it's an organizational mess when 40 people have 40 different ways of submitting the homework. So it really helps me out if you just follow the instructions verbatim. Any other questions? All right, so I'm going to hang out here. I would recommend starting all the labs. And then if you run into issues, so already people are working ahead and saying, oh, this stuff is broken. So I guarantee it worked 3 weeks ago, but I completely understand when people say it's broken, because changes happened last week that broke several of my labs. So if you find something broken, let me know so I can fix it for everyone else who's about to go through the same pathway. I'm trying to fix things as quickly as I can as they come up. Okay, so yeah, I'll just hang out here until 8:30. Otherwise, yeah, I'll let you all get started.